Welcome to 8.6 Intersections of Planes. This is the last lesson for the course. So we've talked about how lines can intersect or vectors can intersect. We've talked about how a vector can intersect a plane and how they can relate one to another, how a point and a vector or a point and a plane can relate to one another. And now we're talking about how two or three planes can relate to one another in three-dimensional space. So before I dive into notes and that, I want you to think about it a little bit. You can get two pieces of paper or else just use your hands as two planes and think about the possible models for the interaction or intersection of two planes in three-dimensional space. I'll give you a hint. When you're dealing with two planes, there are three possibilities. See if you can think of them. All right, well, hopefully you thought of these three possibilities. The first one I think is the easiest probably, is that the two planes are coincident, that they're the same plane, and that every single point on one plane is a solution, is on the other plane also. So every point on the plane is a solution, coincident. The other option would be that they are parallel but distinct. So parallel, they're never going to intersect, just like parallel lines never intersect, in which case there's going to be no solution. And the third option, just like when two lines intersect, they create a point. Here, when we have two planes intersecting, this might have been the hardest one to think about, is that the solution is the set of points on the line of intersection. So if two distinct planes intersect, the solution is going to be a set of points that lie on a line of intersection. You can think about that. I mean, if two planes, if you have your two hands and you place one on top of the other, but kind of perpendicular to it or at a different angle, you can see that there's a whole line, the whole edge of your hand becomes that set of points that are the line of intersection. You can't get it to intersect just at a point. Remember, these planes go on forever and ever in every direction. So this line of intersection also goes on forever and ever in every direction, in both directions. And even if you were to take the blue plane and twist it, all you would be doing was moving that line of intersection. As long as it's not parallel and not coincident, they will intersect, and there will be a line of intersection with an infinite number of solutions, but all of the solutions will follow along that line. And again, so the next example is going to be looking at these three options, example one, and seeing how two planes in a pair of planes intersect or interact with each other. And we're going to do that algebraically by solving them. So example one, we're going to describe how these planes interact with one another. In 1a, we're given plane 1, which is 2x minus y plus z minus 1 equals 0, and plane 2, which is x plus y plus z minus 6 equals 0. So the first thing that we want to look at is, are these two planes parallel to one another, or are they coincident? Basically, are they parallel? So in order to find out if they're parallel, we're going to look at the normal vector for each plane. If the normal vectors are parallel, then we know that the planes are also going to be parallel. So here we go. The normal vector, let's make a note, check the normal vectors. So the normal vector 1 is going to be for plane 1. And I take that from the coefficients of our variables. We've got 2, -1, 1. And the normal vector for plane number 2 is 1, 1, 1. These vectors are not parallel. They're not multiples of each other, and they're not the same. So these planes must intersect. Okay? Since the normal vectors since the normal vectors are not parallel, these planes must intersect somewhere, some way. They're going to intersect. Now, we know that the intersection is going to form a line. Okay, so what we would do is we would basically, normally we would find the point of intersection by using substitution or elimination. But notice now that we have three variables, and we know that the intersection is going to be a line. So we're not going to get a clean, they intersect at x equals this, or y equals 7, or z equals 4. We're going to get an equation for a line. So that equation for a line might involve one of the variables, two of the variables, or all three of the variables in determining what that line looks like. So we are still going to use elimination in order to help us to find the solution, but the solution is still going to involve a parameter or another variable. So let's look at this. We'll make a note. Use elimination to determine the line of intersection. And so I'm going to take our equations of the planes. We're going to label them equation 1 for plane 1. That's going to be 2x minus y plus z minus 1 equals 0. And equation 2 is going to be x plus y plus z minus 6 equals 0. And it's at this point that I would have multiplied one or both of the equations by a constant if I needed to, but I see that I have the same value coefficient, 1 in front of the y and 1 in front of the z's. So I'm actually going to eliminate the z's by using subtraction here. So we've got 2x minus x, that's just 1x. We have negative y minus y, that's going to be negative 2y. Our z's are going to eliminate, cancel out, and then we have negative 1 plus 6 is going to be plus 5 equals 0, and we're going to call this equation 3. Okay, this is 1 minus 2 equals equation 3. And so we don't have a solution yet. We just have another relationship between x and y, and we don't even really know how z plays into it. But we know that x and y relate this way, x, y, and z relate this way, and x, y, and z also relate this way. So what we need to do is express x, y, and z in terms of another parameter. So we're going to introduce parameter t, and that's going to make sense when we write this in vector form. But we're going to introduce parameter t. We're actually going to, it says assign a variable to be a parameter. So we're going to let y equal t. And that's going to allow us to express equation 3 and equation 2 in a different way. So let's look at equation 3 that we just created here, and we're going to let y equal t. That's going to give us an expression for x, okay, in terms of t. So we've got x minus 2t plus 5 equals 0. Then we also have equation 1, which related x, y, and z already. And actually I'm going to use equation 2. Because in equation 2, I could have used equation 1 as well, because there's an equation there that makes sense. But what I'm going to do is use equation 2 to determine what z is in terms of t. Okay? Because now I have an expression for x that involves t. Maybe I should just finish that out. let's just put our final answer over here. We're going to have the intersection. It's going to be the parametric equation, x equals 2t minus 5. And now I have also y equals t, and then I'm going to have an equation for z, and that's going to come from equation 2. So x is 2t minus 5, 2t minus 5, plus y, which is t, plus z, minus 6, equals 0. So now I have 3 t's, and I have negative 11. So I'm going to subtract 3t from both sides, and I'm going to add 11 to both sides, and that gives me my z equation for my parametric equation. All right, let's run through that one more time. And actually, I've been writing them this way, but with our parametric equations, we normally would put the position vector and then the direction piece. So this one is 0 plus t, and this one is 11 minus 3t. Just a little change there, rearranging it. So what did we do? We looked at both of our planes. We checked the normal vector to determine that they are not parallel to one another. Since they're not parallel, they must intersect. We used elimination to help determine the line of intersection. All it did, it gave us a relationship between x and y that didn't involve z. Okay, we could have gotten a relationship between x and z that doesn't involve y. Whatever that did is it allowed us to introduce a parameter, which is going to be that scalar multiple of our direction vector for this line, as you can see over here. We're going to write this in vector form yet. Then we let y equal t, we introduced that parameter, and then we expressed x, we used equation 3 to express x in terms of t, which was right here. And then we have y in terms of t, and in equation 2 that allowed us to express z in terms of t, which means that we have a parametric set of equations. And we could rewrite this in vector form as x, y, z is equal to our position vector, -5, 0, 11, plus some scalar multiple of our direction vector, 2, 1, -3. This is the line of intersection between these two planes. This is the full set of solutions. Okay, and we have it in parametric form, and we have it in vector form. In the second part of example 1b, we are again given two planes. We're given the plane 3, which is 2x minus 6y plus 4z minus 7 equals 0. And plane 4 is 3x minus 9y plus 6z minus 2 equals 0. So the first step, again, is going to be to determine whether or not these are parallel. We're going to do that by taking the normal vector of each plane and analyzing it. So the normal vector for plane 3 is 2, -6, 4. Normal vector for plane 4 is 3, -9, 6. And I'm looking at those, and it looks like if I multiply normal vector 3, each coordinate, by 1.5 or by 3/2, I'll end up with normal vector 4. So what can we say? Since n4 equals k times n3, some scalar multiple of n3, these planes are parallel. Now, are they parallel and distinct, or are they coincident? Are they the same plane? All right, in order to do that, we need to see if there is a solution, x, y, z, that would satisfy both of these equations. Okay, so we're going to use elimination. We're going to eliminate one of the variables and see if we can solve this system of planar equations in 3 space. So use elimination to solve, and we'll just leave it at that. Use elimination to solve. So I set up equation 1 is going to be from plane 1, 2x minus 6y plus 4z minus 7 equals 0. Equation 2 is going to be from plane 4, and I could name them 3 and 4, but here we go. 3x minus 9y plus 6z minus 2 equals 0. I see none of my coefficients line up, so I'm actually going to multiply. I'm going to multiply equation 1 by 3. I'm going to multiply equation 2 by 2. That's going to give me coefficients that are the same value. So I have 6x minus 18y plus 12z minus 21 equals 0, and equation 2 becomes 6x minus 9y plus 12z minus 4 equals 0. And I'm going to subtract equation 2 from equation 1. That's going to give me 0x. Oh, I didn't do this one. 9 times 2 is 18. Negative 18 plus 18 is 0. 12 minus 12 is 0. Negative 21 minus negative 4 is negative 21 plus 4. That's negative 17 equals 0. What do you think about that statement? This equation can never be true. This can never be true. There is no solution. Therefore, these planes are parallel, which we found out because their normal vectors are the same. They're going the same direction. These planes are parallel and distinct. So one plane is above the other or beside the other, or whatever they are. They're going the same direction, but they're distinct. In example 1, part C, we are given plane 5, which is x plus y minus 2z plus 2 equals 0. And plane 6, which is 2x plus 2y minus 4z plus 4 equals 0. And again, we're going to test whether or not they are parallel. So we've got the normal vector for plane 5, which is going to be 1, 1, negative 2. And we've got the normal vector for plane 6, which is 2, 2, negative 4. They are scalar multiples of each other. N5 equals k times N6. You'll notice it doesn't matter which one I write where. There is a multiplier that I can take N6, even though they're bigger numbers. I can multiply it by 1/2 to get the coordinates of N5. So it doesn't matter which way I really write this. It's true both ways. So again, these are either parallel and distinct, or they are coincident. They are the same plane. So in order to check that, I could do substitution elimination again. But I'm noticing that if I take this coefficient, multiply it by 2, I get that one, multiply by 2, I get that one, multiply by 2, I get that one, and multiply by 2, I get that. The constant is going to be using the exact same scalar. It's going to be consistent. So that actually tells me that they are indeed coincident, okay? And let's just make a note of that. So if we had two equations, and we called this equation 2 and this equation 1, then we could use what we've just talked about here. Since 2, equation 2, can be simplified resulting in equation 1, the planes are coincident and every point on the plane is a solution. So in a sense, the entire surface of the plane is the intersection, or the plane of intersection. They are coincident. Okay, that wraps up talking about two planes in three-dimensional space. But what about if we had a system of 3 planes? You can grab your pieces of paper or just kind of think about how could 3 planes possibly interact? There are a number of possibilities. Think through that for a sec. All right, so when we're dealing with a system of 3 planes, we can categorize them or talk about them using one of 2 words. They're either consistent or inconsistent. So when 3 planes are being talked about at the same time, the system can either have one or more solutions, so there is a solution, which can either take the form of a point, a line, or an entire plane, or they are inconsistent, in which case the system has no solution. And that can either mean that they're parallel and distinct, 2 are parallel, 1 is not, or pairs of planes intersect, but not all 3 at one location. So again, this is just to show us that systems of 3 planes can either be consistent, in which case there's one or more solution, or inconsistent, in which case there is no solution. So this is what it looks like. This is what it looks like if they are consistent. There are 3 possibilities. They can either intersect at one point. So again, you can twist and turn any of these 3 planes, the green, the blue, and the orange. And as long as 2 of them don't become parallel, or I guess as long as 3 of them don't all become parallel, then you're going to end up with that one point of intersection in the middle. You can see how green and blue intersect at a line. Blue and red intersect at a line. And green and red intersect at a line. And those 3 lines intersect at a point. Okay, what else could happen? Well, they could intersect and create a line of intersection, in which case it's almost like one of these planes is just spinning around and around and around that line of intersection, creating an infinite number of other planes that all have kind of this axis that they spin on. In this case, the normals are coplanar. So you could picture a normal coming out at a right angle along the red guy and a normal coming out along at a right angle along the blue guy, and then a normal coming out at a right angle along the green guy. And if you actually spun that normal around, you would create a plane. So these 3 normals are all on the same plane. So the normals are coplanar in this case. Here, the normals are not parallel and not coplanar. This is more of a randomized situation. And the third option for consistent, a system of 3 planes being consistent, is the planes are coincident. They lie on top of each other. The normals are parallel, and every point on one plane is on the other 2 planes. So every single possible point on a plane is the solution for the system of equations. Now, what if they don't intersect at a point, a line, or on a plane being coincident? Then they are inconsistent. So the three possibilities for a system of three planes that is inconsistent is that all three planes are parallel and distinct from one another, okay? And actually only two of them need to be distinct. Like you could have plane 1 and plane 2 being coincident. The red plane and the blue plane could be the same plane. They're not in this picture, but they could be. And as if green is removed from them, parallel but distinct, then the system has no solutions, because a system has solutions only if all three equations are satisfied by the same coordinates. Okay, so three planes, parallel but distinct, or at least two of them are distinct. The second option is you have two parallel planes, and then the third one cuts across them, and that's going to happen whenever that third one is not parallel. And then the last option is that pairs of the planes intersect. So green clearly intersects blue, forming a line. Blue intersects red, forming a line. Green intersects red, forming a line. But they never meet at the exact same point like they did in the previous slide. So here the normals are still coplanar, but the normals are not parallel. So when we get into our examples, a couple of the tools that we need is we're going to be talking about the normals, because that's going to be a defining factor for whether or for how these things interact, how the planes interact with one another. So we're going to be seeing if normals are parallel. Okay, are the normals parallel? And that one's pretty easy. We just need to check that one normal is going to be a scalar multiple of the next normal. So if that's true, then the normals are parallel. Okay, and that means that the planes are at least parallel and maybe coincident. Second thing we need to know is, are the normals coplanar? So normals can be parallel and not coplanar. So we need to know if they are coplanar or not. And to do that, we're going to use the triple scalar product. Use triple scalar product. What does that mean? Well, we're going to take the dot product of n1, n2, and the cross product of n2 and 3. And we remember that we have to do the cross product part first, because this will result in another vector. And then we'll take the dot product of n1 and that cross product. If we did n1 dot n2 first, we'd end up with a scalar, and it's nonsense. A scalar cross a vector makes no sense. So the only way this makes sense is if you do the cross product first, and then you'll have two vectors still, and you can take the dot product. Now there's a note here that helps us make sense of why this works. When we learnt to use the triple scalar product, we talked about it as giving the volume of a parallelepiped. So volume, think about that. This is going to give us the volume of some three-dimensional object. Now, what happens if this results in 0? Well, if the volume is 0 of a three-dimensional object, then it must not be a three-dimensional object. It must actually be a flat object with no volume, which means it lies on one single plane. That would make these normals coplanar if the volume of this solid was 0, okay? And likewise, if we don't get 0 from this triple scalar product, then we know that they are not coplanar, because there is a depth, a height, a depth, and a width, okay? Right, there's our figure, something like that, down, across, down. I don't know how to draw it, but you get what I'm saying. So, for example 2, solving systems with 3 planes. For each set of planes, we're going to describe the number of solutions and how the planes intersect. So the number of solutions is going to be either 0, 1, or infinite. And if they intersect, we're going to determine if it's a point, a line, or coplanar. And so here we go. Here's plane number 1 is going to be 2x plus y plus 6z minus 7 equals 0. Plane 2 is 3x plus 4y plus 3z plus 8 equals 0. Plane 3 is x minus 2y minus 4z minus 9 equals 0. Step 1 is to get the normals for each plane. So the normal for plane 1 is 2, 1, 6. The normal for plane 2 is 3, 4, 3. The normal for plane 3 is 1, negative 2, negative 4. Now a quick look at the normals. None of them is a scalar multiple of any of the others. So the normals are not parallel. None of the normals are parallel. So the planes are not parallel. So none of the normals are parallel, therefore the planes are not parallel, so they're not going to be coincident. What we need to figure out, they're going to interact, they're going to intersect, but are they going to intersect at a point, or are they going to intersect along a line? Remember, if they are going to intersect along a line, then the normals are going to be coplanar. That was the picture where you had a line going through and there was a plane here and a plane like this and a plane like this. And they're all spinning around this line, right? And the normal going this way and the normal going this way and the normal going this way were all coplanar. You could spin that normal around and you'd hit the other normals. Or are they going all 3 different, totally different directions, in which case they're going to only intersect at a point. In that case, the normals would not be parallel or coplanar. So we're going to check to see if our normals are coplanar. Are the normals coplanar? And in order to check that, we're going to use our triple scalar product. N1 dot N2 cross N3. All right, so we've got our vectors, and here we go. We're going to just copy them down. We've got N1 is 2, 1, 6 dot N2, which is 3, 4, 3 cross N3, which is 1, negative 2, negative 4. Remember, we're going to take the cross product first. I'm not going to draw the little demonstration on the side. We're just going to take the cross product. If you need to look it up, you can go back into previous lessons to figure that out. So the cross product of N2, N3 is negative 10, 15, negative 10. To take the dot product of this, I've got 2 times negative 10, which is negative 20, plus 15 minus 60, which gets us negative 65. All right, looking back at our notes, since N1 dot N2 cross N3 does not equal 0, They are not coplanar. They are not coplanar. Therefore, the planes intersect at a single point. Next step, where is that point? We're going to just work with two of the planar equations in order to eliminate one of the variables. So I'm going to take equation 1 and 2, but equation 1 I'm going to be multiplying by 4 in order to eliminate the y variable here. So we've got equation 1, which I'm multiplying by 4. It's going to give us 8x plus 4y plus 24z minus 28 equals 0. And equation 2 is 3x plus 4y plus 3z plus 8 equals 0. I'm going to be subtracting. It's going to give me 5x plus 21z minus 36 equals 0. And because I already have 1, 2, 3 equations, I'm going to call this equation 4. Now, this still has two variables in it, okay? So this is helpful. I've eliminated one of the variables. I've eliminated y, and I have an expression relating just x and z, and this statement is true, okay? It doesn't mean that there is no y involved in the solution. It just means I've created a fourth equation that is true. Now, I still have two variables. So I actually, in order to solve this, I need another equation with two variables in it, the variable x and the variable z, so that I can then solve that system of equations. So what I'm going to do is I'm going to do the exact same thing that I did with equation 1 and 2. We're going to do that with equation 1 and equation 3. Okay, so I want to eliminate the y's again. So it looks like I'm going to need to multiply equation 1 by 2 in order to eliminate the y's. So I got 2 times equation 1. That's going to give me 4x plus 2y plus 12z minus 14 equals 0. And equation 3 I can copy down is x minus 2y minus 4z minus 9 equals 0. I'm going to add those because I have opposites here as my coefficients for the y. So I've got 5x's plus 8z minus 23 equals 0, and we're going to call that equation 5. So now I have two equations, and they only have x's and z's in them. So now I can actually solve for one of those variables using equation 4 and equation 5. I see that they both have 5x. So I'm going to take equation 4, which is 5x plus 21z minus 36 equals 0. And actually I'm going to add 36 to both sides. And here I'm going to take equation 5, which gives me 5x plus 8z equals 23. I'm going to subtract those. That's going to eliminate my x's. 21 minus 8 is 13 z's. 36 minus 23 is 13. Therefore, z equals 1. All right, that was great. So again, we had two equations with 3 variables. I cannot solve that. However, I can eliminate one of the variables. That leaves me with an equation with 2 variables. I need to do that again using my original equations in order to create a second equation using the same 2 variables. This statement is true, this statement is true, therefore, where these things intersect, this x is equal to this x, this z is equal to this z. That allows me to use elimination to find out what z that is. Now, how do I find my x? Well, I'm going to use the equations that I created here. in order to find, I'm going to use this equation, equation 4. So I'm going to sub this into equation 4 in order to find x. We've got 5x plus 21z, which is now 1, equals 36. This is 21, so I'm going to subtract 21 from both sides. It's going to leave me with 15. X equals 3. Now that I have z and x, I can go into equation 1, 2, or 3 in order to solve for z. So I'm going to go into equation 1, and it says 2 times x plus y plus 6 times z, that's ugly, minus 7 equals 0. So we've got 6 plus y plus 6, that's 12, minus 7 is 5, so I'm going to subtract 5 from both sides. Y equals negative 5. All right, so these three planes form a consistent system, and that means there is some form of intersection. We know that it's a point of intersection because the normals were not parallel and not coplanar. And then we found the point of intersection. And we'll just write a final note here. Therefore, these planes intersect at the point x, 3, y, negative 5, z is 1. And again, it doesn't matter really which variable you solve for first. We could have eliminated the z's right off the bat or the x's right off the bat, and we would have come up with the exact same solution. So that's one way that three planes can interact with each other in 3 space. Example 2b. We are given the planes plane 4, plane 5, plane 6. Plane 4 is x minus 5y plus 2z minus 10 equals 0. Plane 5 is x plus 7y minus 2z plus 6 equals 0. Plane 6 is 8x plus 5y plus z minus 20 equals 0. And we're going to start this off the same way that we did before. We're going to use the normal vector of each plane in order to make some connections. So we've got the normal vector for plane 4 is 1, negative 5, 2. 1, negative 5, 2. Normal vector for plane 5 is 1, 7, negative 2. Normal vector for plane 6 is 8, 5, 1. And we're going to take a look at those and see if they are scalar multiples one of another. It doesn't look like any of them are. There's no value, there's no constant that I can multiply normal vector 4 by to get the values in 5 or 6. Nothing that I can multiply 5 by to get 6. So none of these are parallel. Since no normal vectors are parallel, what does that tell us? No planes are parallel. No planes are parallel. Okay, so these are going to intersect, but we're going to figure out how they are going to intersect. Are they going to intersect in a line? Or are they going to intersect at a specific point? So the way to check that is to check if the normals are coplanar. Are the normals coplanar? If they are, then the triple scalar product will be 0, okay? So let's go for that. N4 dot N5 cross N6. Write out our vectors. We've got 1, negative 5, 2 dot 1, 7, negative 2 cross 8, 5, 1. So again, we have to take the cross product first. So I'm just going to copy down normal vector 4 dot, and the remainder here is the cross product of vector 5 and vector 6 is simplified to 17, negative 17, negative 51. Take the dot product of those, you get 17 plus 5 times 17 minus 102, and that's 0. All right, so the normals are coplanar. Therefore, well, let's do this. The normals are coplanar. Therefore, and the planes intersect at a line. But I missed, in my explanation, I missed another possibility. The possibility that even if the normals are coplanar, that does not mean that they all intersect at the same line. It could be that 2 are intersecting, and then 2 are intersecting, and then 2 are intersecting. Okay, these are lines, but you can kind of picture that they have a plane behind them. Anyway, so I missed that. So they could still be coplanar and still not all intersect at the same place. They either intersect at a line or not at all, in which case they would intersect independently as pairs. And this I can check using the same strategy as before, substitution and elimination of 2 of the equations, and then another set of 2. That will give me 2 equations with only 2 variables. Right now I have 3 variables in each equation, and then I'll be able to see if I can satisfy the requirements of that equation with a certain parameter. So here we go. We're going to take equation 4 and equation 5. And I notice right away that their x's are both 1, so I'm going to be eliminating x this time around. So I have x minus 5y plus 2z, and I'm going to go ahead and put my constant on the other side, add 10 to both sides. 5 is x plus 7y minus 2z equals negative 6. I'm going to subtract 5 from 4 to create equation 7. 0, negative 5 minus 7 is negative 12y. 2 plus 2 is 4 plus 4z equals 16. And I'm going to go over here and I'm going to use equation 5 and equation 6, but I'm trying to eliminate x. So I'm going to need to multiply equation 5 by 8. All right, so we've got 8x plus 56y minus 16z plus 48, and I put that on the other side, so I'm going to subtract 48 from both sides. And equation 6 is 8x plus 5y plus z equals 20. Again, I have the same sign in front of my x coefficient, so I'm going to be subtracting. That's going to give me 56 minus 5 is 51y minus 17z equals negative 68. Now I have 2 equations. I'm going to label this guy equation 8 and 2 variables. Now I know these equations are true because I created them by using other equations that are true, and I added and subtracted them. That's always going to create another mathematical statement that is true. Okay, so what I'm saying is that if I find a z and a y that satisfy both of these equations, I can be sure that it also will satisfy equation 5, equation 6, equation 4, and that it will give us a solution for our intersection of planes. If I cannot find a solution for this new system of linear equations, then there is no intersection. Okay, there is no x, y, z or a line that these planes intersect at. So here we go. I'm going to set these up, and I'm going to be eliminating the y's, I guess. You'd figure out that I have to go all the way up to 204y and negative 204y in order to find a common multiple. If you wanted to deal with smaller numbers, you could eliminate the z's, find the lowest common multiple of 4 and 17. That's going to be 68. So you could do it that way as well. Either way, we're going to take equation 7. We end up having to multiply it by 17. And we're going to take equation 8, and we have to multiply that by 4. So again, you could just look here and say, okay, if we multiply this by 17, we multiply this by 4, then we'll get the same value in front of the z. It'll be 17 times 4z and 17 times 4z. One will be positive, one will be negative. So here we go. We've got negative 12 times 17. That's negative 204y. We've got 68z equals 272. Here on equation 8, we have 4 times 51, which is 204y, minus 68z equals negative 272. And you can see what's going to happen here, but I'm going to add these because my signs are opposite in front of my z's. What ends up happening is I have 0y, they eliminate out. I have 0z equals 0. So what does z have to be in order to have z times 0 equals 0? Well, z can be anything. So this is true for all values of y and all values of z. And since it's true for all values of y and z, that's going to tell me that these guys meet at a line, and I can determine the equation of that line. Okay? Since this equation is true for all values of y and z, these three planes intersect in a line. So last thing is finding the parametric equation for the line. I'm going to create some space, I think, here. Maybe I can split it up 1, 2, 3 in sections here. So our step here is to determine parametric equations for this line. We're going to let z equal t. That's going to allow us to express each of our coordinates in terms of t. Okay, so from equation 7 right here, we have a relationship between y and z. So from equation 7, we are going to get negative 12y plus 4z, and z is now equal to t equals 16. I have negative 12y equals 16 minus 4t. Now divide both sides by negative 12. I'm going to end up with y equals negative, so I'm dividing both sides by 12, so I'm going to have 4 over 3 plus 1/3 t. 4 divided by 12 is 1/3. Okay, so there's our equation for y. In order to find our equation for x, I'm going to use equation 5 So in equation 5, and this one's a little bit longer, so I'm probably going to have to scoot over there, but that's okay. Equation 5 is x plus 7y, and now I know 7y, I know y can be expressed in terms of t as negative 4/3 plus 1/3 t minus 2z, and I know z is t, equals negative 6. So expand and simplify. This is going to get me 7 times 4 is 28. That's going to give me negative 28 thirds plus 7/3 t minus 2t equals negative 6. At this point, it might help you to multiply every term by 3. That won't change the value of the equation or the truth claim here, but it will make the numbers easier to deal with, and then you can continue to solve for x. For me, I'm just going to think of my 2t in terms of thirds. So this is going to be 6/3, and this is going to be 18/3 as we're working through this. So I've got x over here. I'm going to add 28/3 to my negative 18/3. Okay, that's going to give me positive 10/3. And I also have 7/3 minus 6/3 t. That's going to give me 1/3 t. And that is my expression for x, which means our parametric equation for the line of intersection is, and maybe I should write that. I guess determine parametric equations. We're working across. Let's just keep on going. X equals 10/3 plus 1/3 t. Y equals negative 4/3 plus 1/3 t. And z equals t. And we could write this in vector form also. That would be the vector x, y, z is equal to position vector 10/3, negative 4/3, 0, plus some scalar multiple, t times 1/3, 1/3, 1. Quick review before moving on. We got our 3 planes, we got our 3 normal vectors, we determined that the normal vectors were not parallel, therefore the planes are not parallel, so we took the triple scalar product of our normal vectors and determined that they were indeed coplanar. If they were to create a solid, the volume would be 0, so they are all on the same plane. But that meant that they could potentially, the normal vectors, remember, they could, that means the planes could intersect at a line or not at all. They might intersect in pairs. How did we figure that out? We used our process, our elimination, substitution and elimination with 3 variables in order to eliminate the same variable in 2 pairs of equations. And then we used those 2 new variables to solve for the variables that were left, z and y, and it turned out that z and y could be any values, and the equation would still be true. That told us that the 3 planes intersect in a line, at which point we needed to create that line or figure out what that line was. So we expressed z in terms of t. That allowed us to express y in terms of t and x in terms of t. That allowed us to write a parametric equation and a vector equation for the line on which these 3 planes intersect. Example 3, we're going to be looking at, we're being told that it's going to be inconsistent solutions. So these are not going to have a point of intersection or a line of intersection. They're not going to be coplanar, but we are going to talk about the 3 possibilities that they could be, right? They could have 2 that are parallel or coplanar and 1 that is not. They could have, actually they 2 wouldn't be allowed to be coplanar. They would be parallel and distinct. And then the other one would cut across both of them, in which case there would be no solution. They could intersect in pairs, or they could all be parallel, in which case they would never intersect any of them with another one. So we're going to figure out what's what here. We're looking at A. They give us a system of planes, a system of equations. So we have 3x plus y minus 2z equals 12, x minus 5y plus z equals 8, 12x plus 4y minus 8z equals negative 4. First step, as always, find the normal vectors for each of these. So we have a normal vector, call it n1. This is going to be 3, 1, negative 2. Normal vector 2 is 1, negative 5, 1. Normal vector 3 is 12, 4, negative 8. And a quick look at those tells me, I see some connection here. N1 and N3 are parallel to one another, but N2 is not parallel. So N1 is a scalar multiple of N3, or vice versa, but N2 is not. So that tells me that we have two parallel planes. Now, to make sure that plane 1 and plane 3 are actually distinct, we need to look back at the equation. And we can see the relationship between 3 and 12 is multiplied by 4, multiplied by 4, multiplied by 4. And if I took 12 and multiplied by 4, I don't get negative 4. So that tells me these are distinct, okay? Plane 1 and plane 3 are parallel and distinct. Plane 2 is not parallel to plane 1 or plane 3, but it intersects both planes. So this system has two parallel and distinct planes with one plane cutting across them. Done. Example 3b, our three planes are x plus 3y minus z equals negative 10, 2x plus y plus z equals 8, and x minus 2y plus 2z equals negative 4. Step 1. N1, N2, N3. The first normal vector is 1, 3, negative 1. N2 is 2, 1, 1. N3 is 1, negative 2, negative 2, positive 2. And we take a look at those. We can see none of them are parallel. Nothing parallel. Okay? No parallel planes. So check coplanar. Check the normal vectors to see whether or not they are coplanar. In order to do that, we're taking the triple scalar product here. N dot N2, N1 dot N2 cross N3 equals, copy down my vectors, 1, 3, negative 1 dot 2, 1, 1 cross 1, negative 2, 2. Take my cross product first. So I copy down 1, 3, negative 1 dot. Cross product here is 4, negative 3, negative 5. And the dot product of those is 0. All right, so since the triple scalar product of the normal vectors is equal to 0, that tells me that the normals are coplanar. The normals are coplanar. Normals are coplanar. So the planes intersect either in a line or not at all. So do the planes intersect in a line or not at all? Now we know, because we're going to be dealing with inconsistent solutions in this example, that they're not going to end up intersecting at all. But when you're doing your practice problems and when you're seeing problems like this in assignments, you won't know which option it is. So the whole working of it out might look exactly the same, whether it's consistent or inconsistent, okay? Whether it intersects in a line or not at all, you still have to work out the process of substitution and elimination, okay? So we have our three systems, and we're going to solve these systems algebraically to determine if there is a solution. So here's my equations, okay? I am going to eliminate x. So I'm going to take equation 1, multiply it by 2, and I'm going to line it up with equation 2. So this becomes 2x plus 6y minus 2z equals negative 20. Equation 2 is 2x plus y plus z equals 8. Going to subtract to eliminate my x's. 6 minus 1 is 5y. Negative 3z equals negative 28. That's going to be equation 4. Then I'm going to take equation 1 and equation 3 over here. 1 and 3. And the x's, the coefficient in front of x is 1 for both of them, so I don't need to multiply either equation to create an equivalent equation. X plus 3y minus z equals negative 10. X minus 2y plus 2z equals negative 4. Subtracting again. 3 plus 2 is 5y. Negative z minus 2 more z's is negative 3z. And negative 10 plus 4 is negative 6. I'm going to call that equation 5. So now I have two equations, two variables, and hopefully you can see what's going to happen if I line them up. I'm going to have 0y plus 0z equals something that's not 0, but I'm going to do it anyway. So 4, 5, 4 is 5y minus 3z equals negative 28. 5 is 5y minus 3z equals negative 6. I'm going to subtract those. 5 minus 5 is 0y. Negative 3 plus 3 is 0z. That's 0. Equals negative 28 plus 6 is negative 22. Well, is there any value of y or z, or any combination of y or z, that can make 0 equal negative 22? Nope. So this system has no solution. This system has no solution. These planes intersect in pairs, and we're not concerned really where each pair intersects. And if you want to see pictures of these different interactions as we work through, whether consistent or inconsistent, they're on page 485 in your textbook to help give yourself a picture of what you're looking at. Example 3C, last one. Our planes are 4x minus 2y plus 6z equals 35, negative 10x plus 5y minus 15z equals 20, 6x minus 3y plus 9z equals negative 50. Step 1, normal vectors. Normal vector 1 is 4, negative 2, 6. Normal vector 2 is -10, 5, -15. Normal vector 3 is 6, -3, 9. So I'm taking a look at these, and I can see if I compare them just kind of like x, 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 I don't, and y, 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 and z, 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 I don't really see a connection, but it's easier if I look at them across in rows. I see like a 2, 4, 6, where x is double y and z is triple y. And I see that here as well. X is -2 times y and z is -3 times y. And same thing here. X is -2 times y and z is -3 times y. So I actually do have a connection here. These normals are all parallel. So let me write that. I have a situation where, and I'm just going to give you what where they end up being multiplied by, because we need to find a common multiple between 4, 10, and 6, as well as 2, 5, and 3, and 6, 15, and 9. So I'll just write down what it is. 15 times n1 is equal to -6 times n2 is equal to 10 times n3. Therefore, all normals are parallel and the planes are parallel. So now we need to look back at the equations to determine if the planes are coincident or if they're parallel and distinct. So we know that there's a number that I can multiply this by, and this by. Different number here, different number here, different number here, in order to get these parts to all look the same, okay? And we've looked at that that number is 15 times the first one, -6 times the second one, and 10 times the third one. That will get us all the same on the left-hand side. The question then is, will that get us the same on the right-hand side? That's one way to do it. Another way to do it is to divide all of the terms in each equation by a certain value that will also get us the same statement on the left side of each, and then we'll see if the right sides line up. So I'm going to do it that way. I'm going to take equation 1 and I'm going to divide the whole thing by 2. Okay, that's going to give us 2x minus y plus 3z equals 35 over 2, which is, let's go 17.5. Then I'm going to take equation 2, and I want it to come out looking the same as this. So I'm going to divide it by -5. Okay, -10 divided by -5 is 2x minus y plus 3z equals 20 divided by -5 is going to get -4. And equation 3, I'm going to divide by 3. Divide by 3. That's going to give me 2x minus y plus 3z equals -50 divided by 3, which is just under 17. -50 divided by 3. I'll just leave that one as a fraction. Could leave this one as a fraction too to be consistent. And since they don't come out equivalent, these equations are not scalar multiples one of another. That tells us the planes are not, they are still parallel, but they are also distinct. They're not coincident. Okay? Since the equations are not scalar multiples of each other, the planes are parallel, which we found out here. but distinct. So not coincident. All right, that's the end of 8.6. Your practice problems are found on page 491, and you should be able to handle numbers 1 through 14. Thanks for watching.